Now that we know what a radical looks like, now that we've transformed them all over the place, what about the radical or a square root of any function? I wonder what that looks like. So what I want to do here is I want to take an original function here, whether it be something like a squared function like this, and then I want to apply a radical to it. What do I mean? Okay, so look at here. I said the function, which is this, is a square root of any kind of function here. What am I talking about? Here's the original function. Let's say y equals to 2x plus 1. Let's throw that whole thing under a radical and let's see what happens to it. Well, this gotta be fun. Well, the cool thing about this, and I want to show it to you here, is that you can actually, in each case, use the vars function on your calculator to help you graph it. Case in point, let's take a look at this puppy right here, 2x plus 1, and let's see what happens. I'm going to graph it right here, bring up my calculator. So I'm going to put in y equals to 2x plus 1, right? I'm going to show you what the graph looks like on that thing. We're all kind of familiar with it because, after all, y equals mx plus b, and so 2x plus 1 means, yes, there it is, a nice little y-intercept, a rise of 2, 1, 2, a run of 1, and there's our nice, beautiful line that we can draw. Do you remember that from Math 10? Yeah, it's like a recurring nightmare, isn't it? All right, so now I want to bump this back up to Math 30. I want to go over here, and I want to take the radical of this, or the square root of this function. So first thing I'm going to do is I'm going to put in my second square root. Okay, then I'm going to choose my vars. Remember how to do the vars? You can use the alpha part here. Hit alpha, and then we'll go over to, I believe it's either calc or format. There it is. Oh, yes, it's under F4. There we go. Y1, there it is. So I'm going to take whatever was in Y1, I'm going to put it under the radical sign that we've got here, and now let's take a look and see what the graph looks like. And we're going to shop and compare here. Oh my. Oh my, look at that. Very, very interesting stuff. Now, I'm going to pause this for a second. I'm going to go zoom in on this part of the graph, and I want to show you a couple things. So what I did here is I zoomed into -1 all the way out to 2 here. So there's -1 to 2, and then I went from -1 here all the way up to 2 up here. And I want to concentrate on this specific part of the graph for a second because I want to show you a couple things. I want to show you a few of the flaws of the calculator and some of the cool things about the graph. Well, the original graph, if you remember, was this blue line that we've got out here. There's our intercept at 1. Remember, it was y equals to 2x plus 1. We have our intercept at 1, which is very, very cool. We also have an intercept out here, which surprisingly enough, remember, that's an x-intercept, right? So that's when y equals to 0. So if we actually solve for this and put in 0 equals to 2x plus 1 and did a little bit of solving, we've got x equal to -1/2. And that's exactly where this point is at -1/2. Okay, that's interesting. Now, let's shop and compare. Here's the radical function, which is in red right up here, okay? And it's going out that way. Very, very cool. Now, I'm going to clean this up for a second. I want you to see a couple things. All right, so let me just clean it up. Here we go. The thing I want you to see is that this thing, notice how this graph does not touch that axis. That's a design flaw of this calculator. It has to actually come down and touch this axis. It starts on that point of -1/2. Now, watch for that when you're graphing these things because a lot of students will look at this and they'll say, oh my goodness, it doesn't hit the axis there. It can't be. Well, in fact, it does hit the axis right here, and it is there. The other thing I want you to notice is look where the original graph is. The original graph is out here, but look at this section right here. Look at this. Look how this part of this graph right here is above the original, and this part here is now below the original. So it's two different really cool sections until it gets to that point right here. And that's going to be the thing that's consistent with all radical graphs. Okay, so I've told you way too much already. What I want to do is I want to get back to our worksheet here, and I want to start looking at some examples. And then eventually we're going to draw some conclusions from that. Okay, so here we go. Let's look at the first one. This is f of x equals to x plus 1, and then of course we're going to take the square root of this. So let's put this on our calculator right now. So the f of x is x plus 1. Let's go to the calculator, x plus 1. But notice I already have this set up. I already have the setup, and you're going to find out that I'm not going to change that ever. I'm not going to erase that ever. I'm just going to leave it in there because I know I want to take the square root of things as I go. So let's clean that up and let's go. Let's graph it. Zoom standard, zoom 6, there it is. Boom. Notice that you have that little curve thing happening here again. Isn't that interesting? Where the square root, the radical part of the graph, is above the original. That's really, really important to know that. And that happens right in just one little section, which I'm going to describe a little bit later on. Okay, so let's put in a couple things here. One of the other things that I want you to notice is that it starts here at -1. Okay, that intersect here is very, very important as we go through this. So let's answer a couple questions. So our first graph here, of course, is x plus 1. So rise of 1, run of 1, or run down of 1 and 1, and we're going to look something like that. Then our radical part of our graph starts on this point, that x-intercept every single time. And here's that point 1. This is the cool part. This comes over and starts doing that. So you're going to have that little section above, and then after this point, it's going to be below. Interesting. Domain and range. Well, domain for this guy obviously starts at that x-intercept. That x-intercept, of course, happening when y equals to 0, right? Bring the 1 over, you got x equals to -1. Isn't that interesting? Our domain has to be x greater than or equal to -1. Our range, look at this. I want to show you something very, very cool. Take a look at the range for a second. You'll notice something very, very interesting. Radical graphs do not start below the x-axis. Neat. So watch this. Y has to be always greater than or equal to 0. And you're going to see this happening over and over and over again. That's the neat thing about this. Let's take a look at the next one. Take a look at this guy for a second. Let's see if you remember any of your skills from Math 20-1. First thing we notice that it's got to be opening down. It is going to be a parabola, and its intercepts at -1. So you're looking at a graph that starts here, opens downwards, right? Okay. Now, I got a question for you. What's the radical of this? Think about this for a second. Isn't the entire function below the x-axis? So in fact, this entire function will always be negative. Question, can you square root a negative? Well, the answer for that, hopefully, is no, you can't. So the domain for this does not exist. Range for this does not exist. That's right. Some people may argue and say, oh, no, domain exists. In other words, yeah, I suppose you can put any value in there you want. So I guess maybe I'll change that and say x is an element of R, but the range does not exist. DNE does not exist. One of the reasons why is because, of course, there's no such thing as taking a square root. Well, I want to prove that. Hold on. Do you remember what that equation was? It was minus x squared minus 1. Now think about it. If I take the square root of that, will a graph actually appear? Watch. Boom. There's the original, but where's the square root graph? It doesn't appear. And let me prove that to you. All you got to do is go second table and look at all the errors. Error, 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 as far as the eye can see. And the reason why it's error, error, error is because of the fact that all of those values will always be negative. Look at all of these y1 values. Every single one of these y1 values are negative. You can't square root a negative. So guess what? That graph does not exist. Cool. Okay, let's go back to this guy now. A little further. All right. How about a simple x squared graph? This will be really, really cool. You know what they look like, right? There's the 0.11. You know what they look like. You've done these in Math 20 until your fingers bled. Oh my goodness. There we go. Should look like that, shouldn't it? My question then is, I wonder what the radical of this function is. Well, let's put it in our calculator. All right, x squared. Okay, let's graph it. Boom. Oh, cool. Notice how you have the original graph here in blue. There's our parabola, but look at this same thing happens again, where this guy is just slightly above and then suddenly starts going out this way. Slightly above and then starts going out this way. It's very interesting how a section of this graph is slightly above. Very, very neat. So can we write a domain and range for this guy? Absolutely. We'll go here and say this is slightly above, and then it goes out that way, and then goes slightly above and goes out that way. So the domain in this, because everything is above x is an element of R. The entire green graph, this original guy, is all either touching the x-axis or above the x-axis. So what's the range? Range, of course, look at your red graph here, right? Look at your red graph here. It has to be greater than or equal to 0 again. Interesting. You know that because of the fact that your range has to be positive. Okay, so what happens when we deal with a cube? Remember what a cube looks like. A cube is one of those guys that comes down here like this and kind of just sections off that way. Do you remember that? I wonder what the radical function for that's going to look like. Well, let's take a look. I still have the squared in there, so what I'm going to do is I'm going to just change that to a cube. There it is. Hit the graph. Boom. Aha. Oh, interesting. Same kind of idea happens. That radical is slightly above until again we get to that point, which is a very interesting point we're going to talk about an awful lot as we go on with these podcasts. That's very, very cool. So this guy, in fact, again, kind of does this. Doesn't have that bend going outwards. It's kind of got a bend going inwards. But notice again, this section of the graph is negative. So guess what? On the radical, it does not exist. So your domain has to be x has to be greater than and equal to 0. And the range, of course, is still greater than or equal to 0 because whenever you square root a number, you get a number of value greater than 0. Okay, so let's keep going here. How about absolute value? That should be pretty cool. Well, let's do the same thing. Go into our calculator here. And if you remember how to do absolute value, that's going to hit alpha and you're going to hit F2 here. Absolute value shows up right away. Boom. And then just put absolute value of x. Let's graph it. Here we go. Boom. Oh, neat. Same thing happens again. That little section is above the original graph again, and it seems like right at 1. It looks like it's always going to be at this value of 1. That from here, from the original to here, is always going to be above, slightly above the original graph. Neat. Okay. And then after this point, that graph is now below the original graph. Very, very interesting. Okay, so let's go back and fill in all our tables here. So absolute value we know, boom, boom, comes down, looks like that. The big V there, okay, perfect. And then again, we're starting at here, a little curve up, and then away we go. A little curve up above the graph, and away we go. So our domain here is an x is an element of R. Why? Because, again, all the values of our original graph are above the x-axis. Range, same thing. Wow, interesting. But what happens when you get a guy like this, x squared plus 4? Do you remember this from last year? Right, this is an intercept. 1, 2, 3, 4. X squared means it's going to go look something like that. Well, honestly, let's think about this for a second. Let's think about this for a second. We started at this point right here, right? We started at 4. This just means take the square root of it. So what is the square root of 4? Oh, that's easy. That's 2. But what you're going to notice here is that every one of these points is got to be square rootable. You should be able to square root every one of these points. So these points are actually going to be the square root of whatever that y value is here. So if you think about it, I'm going to predict this to kind of go in that kind of shape. It's not going to have a bend, and this is one of the only graphs that does not go above the original graph. The reason why is because of the fact that the intercept is way up here. Now, so I'm going to say right now that our domain is going to be a value of R, and our range, of course, is going to be greater than now and equal to not 0 this time, because if you look, there's really nothing here, right? This particular graph starts on whatever the intercept is. Oh, and it's not just the intercept, it's the square root of that intercept. So in fact, it's greater than or equal to 2. Neat. Oh, let's prove it. Let's put it on the graph. I got it in there for you already. Graph it. Boom. Just as I predicted. Neat. Okay, so let's go back to here now. Let's take a look at the very last one, which is this guy out here. What if x squared minus 4? So in other words, the intercept is way down here at, oh, 1, 2, 3, oh, went one too long. There we go, minus 4. Now, the cool thing is let's find out what the x-intercepts are as well. Think about this. The x-intercepts happen when y equals to 0. So x squared equals to 4. Remember the square root principle? Plus or minus 2. So at 2 and 2. So our original graph should look something like that, right? There's our original graph. But look, there's a section of the graph that's below the x-axis. And one of the things that we've noticed so far, whenever you take a square root of something, it always seems to start on whatever the x-intercept is, and then curves and goes out that way. I'm predicting now, based on the knowledge that I have on the previous graphs, that's what this is going to look like. Okay, hold on. You can see that I've changed that for you. Let's graph it. Let's see if I get exactly what I predicted. You bet I did. There it is. And the fact that this is slightly over again, boom, slightly over again, boom, and it does hit the x-intercepts. So let's draw a little conclusion here. First things first, domain on this guy. Well, x has to be, of course, less than or equal to -2, and x has to be greater or equal to 2 here. What's the range? Wow, never seen that one before. Okay, so let's make a couple of last little conclusions here regarding what we've just learned. This ought to be interesting. Okay, so what's the shape? Well, it's usually a curve, right? It's usually a curve, right? It kind of looks like that. Now, obviously, it can go open that way or open that way. It just depends, okay? It's always x-intercept and above. Oops, and above. Right? Okay, perfect. Okay, you also notice it's got a couple of invariant points. The invariant points happen there, and surprisingly enough, when y equals to 0. So at x, comma 1, that's that value of 1 that we see where the graph is above the original, okay? And of course, at x as an element to 0, this being our x-intercept. Those are two very, very common things that we see. Okay, now the other thing that we have to put down here is the fact that there are no negatives. That doesn't exist. So that means then that you do not have a graph of a radical function anywhere in this area down here. So in other words, y always has to be greater than or equal to 0. Really, really cool stuff. I know this was a long podcast. I apologize for that, but boy, I tell you, you're going to learn a lot from this one.